Having seen in the previous chapter, number 2, the basic concepts in estimation, we can start and carry out at this stage linear estimation in static systems. We'll bring a number of examples and end the chapter with real-world examples. With a real-world example, and this is the following, as follows. Okay. The objectives of this chapter will be the minimum mean square error estimation for Gaussian random vectors. It will be number 1, fundamental equation of linear estimation that will be the basis for subsequent development of estimation in dynamic systems. We'll discuss the linear MMSE estimator for arbitrarily distributed random vectors. Not the whole world is Gaussian, therefore we need other techniques that apply to non-Gaussian models. We'll carry out the least squares estimation of an unknown constant vector from linear observations. We'll show the batch form and then go on to the recursive form that is the basis for the dynamic estimator. And we'll have 2 applications for the least squares technique. Polynomial fitting will be one, and the second will show how to choose the order of a polynomial when fitting a set of data points. And the illustration of a nonlinear least squares solution to a practical problem. It is a source of radiated energy that is moving, and we want to localize it using bearings only or passive sensor measurements. First, the estimation of Gaussian random vectors. We are interested in the conditional mean and the conditional covariance of a Gaussian random vector given another Gaussian random vector. So we take x and z, which are jointly Gaussian, each is a vector, and we stack them, x and z stacked, now make up the vector y, and we'll say that y is Gaussian distributed with mean y bar and covariance py y, where the mean y bar is just the stacked vector of the means x bar and z bar, and the covariance matrix of y has blocks pxx, pzz diagonal blocks, off diagonal pxz and its transpose pzx. So we show now the partitions based on the partition of the vector y, same as y bar. The first block of pyy is pxx, the covariance matrix of x. Pxz is the covariance, sometimes called cross covariance, between x and z, which is the transpose of pzx. And x will be our random variable to be estimated, and z is the measurement or observation. So starting from this result that they are jointly Gaussian, we're going to estimate x in terms of z. We have seen before that the estimate of a random variable x in terms of another random variable z according to the minimum mean square error, the MMSE criterion, and this is the MMSE estimator, is the conditional mean of x given z. Now, if x and z are jointly Gaussian, as we assumed at the beginning of this formulation, the conditional mean is x hat denoting E of x given z is x bar, the unconditional mean, plus the covariance between x and z times the inverse of the covariance of z times z minus its mean. And then we have a conditional covariance matrix of x, pxx given z, the expected value of x minus x hat, and this is the x hat which comes up here, times x minus x hat transpose given z is the unconditional covariance minus pxz, pzz inverse, pzx. And this was obtained earlier in 1.4.14 with a complete proof in the textbook. Now, the result that we have follows from the fact that the conditional PDF of x given z is also Gaussian. Remember, the conditional mean is the expected value of x with respect to the conditional probability density p of x given z. So integral x p of x given z dx. And a similar expression gives us the covariance. So, and the fact that this conditional density p of x given z, shown in 1.4, is Gaussian is the key result. Now, this, if everything is Gaussian, we have expression. Now, unfortunately, the world is not all Gaussian, so we are interested in a solution that is linear and satisfies the minimum mean square error estimation, an important feature of the solution obtained or shown a moment ago for the Gaussian random variable situation is that the expected value of x given z is linear in z. So let's see if we can obtain a similarly simple and convenient solution for the non-Gaussian case. So what we have is, in general, regardless of the distributions of the random variables, the MMSE estimate is E of x given z. But if we don't know the densities, because they are not Gaussian, or even if we know them, but not being Gaussian, it might be too complicated to evaluate E of x given z exactly. So, it is either not known or too complicated. Therefore, we are interested in a method which is simple, namely yields the estimate as a linear function of the observation or observations and requires little information. With how little can we get away? It turns out we can get away with the first and second moments, which is somewhat similar to what the result in the Gaussian case turned out to be, because obviously a Gaussian density is defined in full by first and second moments. So we assume things are not Gaussian, but we have the same first and second moments, and let's see how we can obtain the result. The resulting algorithm is called linear minimum mean square error estimation. It relies on what is known as the so-called principle of orthogonality. Namely, the best linear estimate in the sense of minimum mean square error of one random variable in terms of another random variable, again, no Gaussian assumptions. The second random variable is the observation or observations, will be such that we have two properties. Number one, the estimate should be unbiased. The estimation error has been zero. Makes sense. The estimation error is uncorrelated from the observations. And we'll see that this concept of uncorrelatedness has a geometric counterpart, orthogonality. And we'll discuss the linear MMSE estimation for zero mean random variables. This can be easily generalized to the non-zero mean case, just shift the means. Now, this linear MMSE estimation will be formulated in terms of what is called a normed linear space of random variables as follows. Let's consider the set of real-valued scalar zero-mean random variables, Zi. Take n of these Zi's. It turns out they can be looked upon as vectors in an abstract vector space or linear space. What is a linear space? It's a space, so-called, closed under addition of its elements and multiplication by scalars. By this we mean that any linear combination of two random variables or two elements of our space is another element in the same space. So that's the closeness under addition and multiplication by scalars. This is what we do when we take linear combination. We multiply them with some scalar number and add them up. A complete vector space in which one defines an inner product is called the Hilbert space, and we'll define an inner product between two elements of this space, Zi and Zk, this is the inner product symbol, as the expected value of their product. And the question is, does this inner product meet the requirements of the inner product of a vector with itself being a norm squared? It turns out it does. It's zero only if it is the zero vector. You multiply the vector by scalar, the norm squared is multiplied by the square of that scalar. So what we have as an inner product is a valid definition from the point of view that it does define a norm of a vector. And now we can call two vectors as orthogonal, and we denote it as Zi orthogonal to Zk, when Zi, Zk, their inner product is zero. It is equivalent, however, because of the definition of the zero mean random variables that we started with, being just uncorrelated. The expected value of Zi, Zk equals zero means they are uncorrelated because each of them have zero mean. So what we have now is the definition of orthogonality. In a Cartesian space, when you define the inner product of two vectors, say in a plane, they are orthogonal to each other. The inner product, which is product of their magnitude times the cosine of the angle between them at 90 degrees, we say they are orthogonal, and the inner product is zero. So that's because cosine of 90 is zero. Now, the linear minimum mean square error estimator of a zero mean random variable x in terms of the set of random variables Zi, I going from 1 to n, will be a linear combination of these Zi's. And we have to find the betas. So the two conditions were, as we'll see in a moment, unbiasedness and orthogonality. And we'll see how these follow from the fact that we want our criterion to be minimum mean square error. So we define the error. Our estimation error is x tilde, x minus x hat. What is the mean square value? Is the norm of this error. And the norm is the expected value of the square of this quantity, which is the inner product of x tilde with itself. So this is a norm squared, set it to 0. And we are going to use the solution, for the solution to this estimation problem, the linear MMSE estimate, we'll use a circumflex or a hat on top of it, even though it is not the conditional mean. So the hat will denote now just an estimate. Specifically, it will be a linear estimate. So the norm of the estimation error, that's the inner product of x tilde with itself, or the expected value of the square of the error, the mean square error, would be the expected value of x minus this linear combination of the z's to be determined, because we don't have yet the coefficients beta I. So we have to carry out a minimization with respect to the beta I going from 1 to n, and we'll calculate the partial derivatives of this expression, the mean square error, with respect to each beta k, and set this to 0. So take a half minus for convenience, partial of the norm squared of the error, this is the mean square error, expected value x minus beta I, Zi, Zk. So after the first derivative, we end up with this expression, but what do we have here? X tilde times Zk. So the expected value of x tilde Zk, which is the inner product between the error and the observation Zk, has to be 0 for each k. Namely, the error has to be orthogonal to each of the observations. And this is the principle of orthogonality. In order for the error to have minimum norm, and we can think of it as a length, it has to be orthogonal to the observations. And this is equivalent to stating that the estimate x hat has to be the orthogonal projection of x into the space spanned by the observations. Take z1 and z2, our two observations. They define a plane. The vector x is outside this plane. If we project it orthogonally to this plane, the result is denoted by x hat. The difference between x and x hat is x tilde. So what we have is x tilde shortest if this x tilde is orthogonal to the plane defined by z1, z2, or x tilde orthogonal on z1 and x tilde orthogonal on z2. So you can see now from this how this orthogonal projection of our random variable x into the subspace defined by z1 and z2 defines our best linear estimate. And clearly a vector in this plane, the x hat vector, would be, we can express it as a linear combination of the two vectors z1 and z2 which define this plane. Now, if we have vector random variables, we'll consider now a vector valued random variable x and another one z, which are not Gaussian and not zero mean. So from a scalar case, which was not Gaussian, we go directly to the vector case, also not Gaussian, but now we also add the fact that it might not have mean zero. And we are interested in the best linear estimate of x in terms of z. And the criterion for best will be the mean square error that we want to minimize. Now, we want an estimator of the form x hat equal az plus b. This is, strictly speaking, not a linear function, but an affine function, because there's a constant b that will need to guarantee the unbiasedness condition. So we want to minimize a scalar mean square error criterion, namely the expected value of the squared norm of the estimation error, the inner product in a Cartesian space of the vectors x minus x hat with itself, expected value. So this is the mean square value of the error. We denote it by j, and that's what we want to minimize right now. So, from the previous discussion, the linear MMSE estimator has two requirements. The error x tilde, which is x minus x hat, is zero mean, namely the unbiasedness requirement. Second, the orthogonality on z requirement. In other words, x hat, the estimate, will be the orthogonal projection of the vector x into the space spanned by the random components of the observation vector z. Z is a vector, say in a Cartesian space, but its elements are random variables. So we look at this from 2 points of view. One, vector in a Cartesian space. Two, each component of this Cartesian space vector itself is a random variable. So what we have now, number one requirement, the unbiasedness. We calculate the expected value of x tilde, which is really x here, expected value is x bar, x hat being az plus b, its expected value of az bar plus b. We don't know a, we don't know b yet. Immediately we can use this equation to solve for b as if we knew a and substitute it out. So we have the solution b as x bar minus az bar. We substitute it in the expression az plus b, and x tilde now will be x minus x bar minus a z minus z bar. So the second requirement will be imposed now. It's a multidimensional problem. Therefore, each component of the error vector x tilde has to be orthogonal to each component of the observation vector z. And now orthogonality is to be understood in the space of random variables, which means the expected value of the product of two random variables is 0. That's the orthogonality. And we write it in one single equation by setting up a matrix x tilde z prime, z transpose. Each component of this matrix will be a particular product of one of the components of the error with one of the components of the observation vector, and we write it out explicitly, x tilde as x minus x bar minus a z minus z bar from this equation times z transpose. Now remember, this is a zero mean quantity from the unbiasedness requirement that we just posed. Therefore, we can add an arbitrary constant or subtract to the second term. And for convenience, we'll subtract the mean of z bar. That does not change the result because the first term is zero mean. So multiplying it by a constant is still 0. But for convenience, once we add this here, we immediately see that applying the expectation operator, there's an x minus x bar times z minus z bar. That's pxz, the covariance between the vector x and vector z. The E expectation goes past the deterministic matrix A, which we don't have, but now we are almost ready to obtain it. A then will be expected value z minus z bar transpose, but this is nothing but pzz. And this has to be equal to the 0 matrix, so each component of x tilde is orthogonal on each component of z. And this equation 8, if the matrix pzz is invertible, then we can solve it and obtain A as pxz pzz inverse. The invertibility really, as mentioned earlier, for the covariance to be positive definite, you should have no linear dependence among the components, which means you have no z component linearly dependent or linear function of the other z components. That would imply we have too many z's. We don't need all of them. So if one is a linear combination of the others, means that's not an extra piece of information. So we can assume pzz to be invertible and therefore no redundancy in the vector z. So we can combine now these results, and with the vector A being pxz pzz inverse, the x hat is x bar plus pxz pzz inverse z minus z bar. And lo and behold, this is identical to what we found as the conditional mean in the Gaussian case. So our linear estimator really looks like exactly the same one as we had in the Gaussian case, except the Gaussian case was optimal. Here it is only the best linear. The matrix mean square error, it's really not a covariance, even though in most cases it is called covariance. The expected value of x tilde transpose, again, after evaluating from the previous expressions, yields exactly the same as the conditional covariance in the Gaussian case. But now it's really a matrix mean square error, because this is, if things are not Gaussian, it's not a conditional mean. These two equations are the fundamental equations of linear estimation. A number of remarks. We made a distinction between the scalar mean square error criterion, which was an inner product, and the matrix mean square error, an outer product. This is the matrix mean square error is the expected value of an outer product the outer product is in the Cartesian space. The matrix MSE is sometimes called, again, with some abuse of language, covariance matrix. Now, the conclusions we can draw from all this are as follows. The best estimator in the minimum mean square error sense for Gaussian random variables is identical to the best linear estimator for arbitrarily distributed random variables, as long as they have the same first and second order moments. The linear estimator is the overall best if the random variables are Gaussian. Otherwise, it's only best within the class of linear estimators, and for those random variables with non-Gaussian distribution, there is, in principle, a better non-linear estimator, even though it will be hard to find. But there will be one example in which we can show not only what that non-linear estimator is, but evaluate its quality compared to the linear estimator. So this will be done later. Now, in view of this, we can draw another interesting conclusion, namely, the Gaussian assumption can be seen as a worst case in the context of minimum mean square error estimation. From the point of view of minimum mean square error estimation, the Gaussian assumption is the worst case in view of the following. If the random variables are Gaussian, the minimum achievable matrix MSE is still given by equation 8, 3 to 1, 8. If they are not Gaussian, but with the same first two moments, one can achieve with the linear estimator the matrix mean square error 3, 3, 2, 12, which is the same as 3 to 1, 8. But in the non-Gaussian case, if we can compute the conditional mean, being the absolute best as opposed to the best within the class of linear estimators, would give a matrix MSE, really a covariance matrix in this case, better, less or equal to 3, 3, 12. So what we have is there's a possibility of improving beyond that fundamental covariance equation, but only if the random variables are non-Gaussian. Even though it might be complicated, the possibility is there. Therefore, since in the Gaussian case there is no way to improve, it's a worst case. Next, we are going to look at least squares estimation. Now, for non-random parameters, and the first one will be the batch least squares. And we'll look at the linear problem. So this is the linear least squares problem, where we want to estimate an nx dimensional vector x modeled as an unknown constant from a set of linear observations. These are nz dimensional vectors. Zi is h of I plus w of I. And the criterion will be to minimize a quadratic error, that's the least squares, which will be written as quadratic form of the difference between Zi and Hix with respect to a matrix Ri inverse. So this is a weighting matrix, and later we'll come back and we'll see why we denote it as such, because it will have a certain meaning. So what we have is a sum of quadratic forms, positive definite, which means it cannot be 0 unless you manage to get this equal to 0, which we usually will not be able to. And so this is a quadratic error, our criterion. We can come up with a much more compact notation without a summation by stacking all the z vectors into a little z super k, all the H matrices into an H super k, and we'll see on the next page, the R super k is a block diagonal matrix consisting of blocks, the Ri, I going from 1 to k. So this is a single quadratic form of a large, that's a k and z dimensional vector. We have a WK. These are the stacked measurement errors. And the R super K, it's a block diagonal matrix with blocks Ri. It is a K and Z by K and Z, and it is positive definite because each of its blocks has been indicated as being positive definite in the formulation of the least squares problem. Now, once we reduce this problem to its simplest notation, it can be solved by setting its gradient with respect to x. So this is the function we are going to minimize. Del x of jk turns out to be 2h, that's a stacked matrix, transpose the RK, the big block diagonal matrix inverse, the stacked vector of observations little z super k minus h super kx. All this is 0. And we can solve it. Open the brackets here, and the x hat k is hk prime RK inverse hk, the whole thing inverse, hk prime RK inverse zk. Assuming this inverse exists. But RK being positive definite, if you go one step further to check have we accomplished a minimization, you take another derivative, really a gradient, you obtain the Hessian of our cost function j. This will be positive definite, and this is the condition of a multidimensional. The Hessian of my scalar function I'm trying to minimize should be positive definite, and this follows from the fact that in a scalar problem, when you try to minimize quantity, the first derivative is set to 0, the second derivative should be positive, because before 0 the derivative is positive, then goes to 0, then goes before 0, the second derivative positive indicates that the first derivative is first negative, then 0, then positive, so you have a U-shaped curve, and the counterpart of this in the multidimensional case is having a positive definite Hessian. Okay, now what we have is, as far as the vector x is concerned, a batch estimator. Namely, if we have data which keep arriving, I have now a vector z super k of increasing dimension as I get new observations. What we have to do is reprocess the entire data for every k, the cumulative data, which is obviously not a nice thing to do. So we'll see later how to get away from this issue. Before that, we'd like to connect it, the least squares solution, to the maximum likelihood estimator. If my measurement errors, Wi, are independent Gaussian random variables with mean 0 and covariance R of I, they don't have to be identically distributed, might have different covariances, then minimizing the least squares criterion that we set forth is exactly the same thing as maximizing the likelihood function lambda sub k of x, that the joint PDF of all these z's, or the PDF of the stacked vector z super k, which is the product, because they are independent, p of zi given x, and each p of zi is a Gaussian. Don't need a constant right now, exponential, and we have, these are the exponents, zi minus hix transpose Ri inverse zi minus hix. This will be the exponent in each of these PDFs, and because you have a product, the exponents just add up. So you can see that maximizing the likelihood function is the same thing as minimizing the exponent, because it has a minus sign in front of it. Therefore, the two criteria lead exactly to the same result. So least squares again is a disguised maximum likelihood estimator. As we shown in the scalar case, now we have shown the same result for the vector case. Therefore, the least squares criterion really implicitly assumes that the WIs are independent and zero mean with covariance Ri, and would minimize the sum of those weighted norms. Now, what we took as a weighting in the original least squares is really the covariance of the WI in the Gaussian assumption. So, all that can be said is that the least squares is a disguised maximum likelihood technique. If somebody tells you, I don't believe in maximum likelihood, I believe in least squares, since the two are equivalent, it really doesn't make any sense, and that person would really use a maximum likelihood criterion under some assumptions. Now, some of the properties of the least squares estimator will stay still with the batch form because it's easy to see its properties, and later we'll go to the recursive version. So we have the assumption that the WI are uncorrelated zero mean random variables with covariance I. These are assumptions we'll make, no distributional assumptions. We will not assume that they are Gaussian. The first observation is that least squares estimator is unbiased. If you take x hat k, given by the expression hk rk inverse hk inverse hk prime rk inverse hk x plus wk, this is the z here, the z super k. I want to take the expected value. I replace the z super k by hk x plus wk and take the expectation. I pass it past all these deterministic matrices, no problem. If you take the expected value of w is 0, the expected value of hk is hk. So again, E can be passed here, but that's deterministic. So there's no expectation anymore once you got rid of the w because it's zero mean. And this h prime rk inverse hk cancels, and you end up with x back. So the expected value of my estimate is the true value. So I have an unbiased estimator. The estimation error, x tilde, is x minus x hat, and you subtract x hat from x, you end up with h prime minus h prime rk inverse hk inverse, hk prime rk inverse w super k. So the stacked vector of noises is what really becomes the error in my estimation. The reason this is convenient is we can take the outer product of this with itself. The covariance matrix, or mean square error matrix, I indicated that we will not be 100% consistent in the terminology. P of k is the expected value x hat minus e of x hat minus e of x hat, but e of x hat is x. So what we have now is the expected value of x tilde transpose. Here's the x tilde, hk prime rk inverse hk, the whole thing inverse, hk prime rk. Now, here we have a w. From the other one comes a w prime, which after expectation gives an r. And now the same expression transpose, which means take terms in the opposite order. So we use this property, E of W transpose is R. You notice that here R and R inverse cancel. But then we have an H prime, R inverse, H prime, and again another one of the same thing. So the three, there's inverse, as is, and inverse. These two cancel. I end up with the first expression only. So the covariance of my estimator is H prime, R inverse, H inverted. Very important to understand the connection between the existence of the solution and parameter observability. We need the existence of this inverse of H prime R inverse H. Otherwise, there is no solution. If it's not invertible, my covariance is not finite. Not invertible, first, this is positive, at most can be either definite or semi-definite. What we have is, in general, if it's positive definite, will be all eigenvalues are positive. Then it's invertible. If it has a zero eigenvalue, it can have no negative eigenvalues. Then the inverse has some infinite eigenvalues, which means we cannot observe all the parameters. There is a problem of observability. I want the resulting covariance to be finite. I don't want zero eigenvalues here, and I want what is called an observable or completely observable parameter. In many practical problems, we can encounter situations different than zero eigenvalues or non-zero eigenvalues, marginal eigenvalues, near singularities. That will lead to large eigenvalues in the inverse, which is an indication of marginal or poor observability. It turns out there is an eigenvector analysis that can be done in the parameter space, and you can figure out which are the parameters which have poor observability. And we will see some situations where we have better or less good observability in a practical nonlinear problem.